Cool. So yeah, I'm going to talk about an open source library that I'm really excited about, that the company I run and work at invests heavily in, and how it can fit along with federated learning. So I'm going to propose a few ideas here. All right. So today I want to convince you of a few things. One, that federated model training has two pieces to it: the data that goes into it and the models that come out of it. That Hamilton can help you with the data side to collaborate on feature engineering and form contracts for your model's data. Hamilton is easy to get started with and easy to use. Cool. So at DAGWorks, we're making machine learning pipelines easy to manage. Nobody should be afraid to inherit data science code. So trying to solve the problem of people writing sort of crazy pipelines and passing them off to the next person. But I'm not selling you anything in this talk. This is all open source. You can install it on PyPy, get started in a few minutes, try it out. We have this nice website, tryhamilton.dev, and we have plenty of documentation. Here's an example of how you can try it out in your browser. But yeah, what are we going to talk about today? Well, first, I want to talk about the challenges around federated feature management. Then I want to talk about the tool Hamilton that can help make it easier. Talk about how you can apply Hamilton to federated learning, thinking specifically about the Flower framework. Then talk about additional benefits of Hamilton. So sort of what else you get when you buy into this paradigm. And finally, talk about open source progress and updates. Cool. So we're going to do the cross-silo example of federated learning, but it could work with sort of any like cross-device. Devices are generally embedded, so you may or may not want to use Python, but we're going to focus on the cross-silo because it's a sort of interesting problem. But I think it can apply to federated learning generally as well. So the scenario is something really simple. We're using structured medical data to predict diagnoses. The data must stay put. This is where you get Flower. This is where Flower comes into handy. You've got feature engineering on this data to feed models. So maybe it's sort of lightweight, moving the data from one place to another to pass it into something self-supervised. Maybe it's more heavyweight, sort of like figuring out exactly what the features you want are and sharing it with other people. And you want to collaborate across multiple hospitals. These might have data in different shapes. They can't share this data, but they can potentially share code. This is just code. It doesn't contain any sort of like regulation-breaking stuff. Right? So what does this look like? Well, you got all these hospitals. They each have their own set of feature transforms. Then they do local training, and Flower does this feedback loop to update the model weights. All right. So the challenges: how do you collaborate between teams across hospitals? How do you ensure models are trained on correct feature versions? And how do you ensure the data is the same for all your model variants? Hamilton is here to make it easier. I'm going to first talk about the basics, then about how we can apply it to federated learning to solve this problem. So the idea here is, what if every feature corresponded to exactly one Python function? And then what if the way that function was written told you everything you needed to know about the feature it created? So in Hamilton, the artifact, feature in this case, is determined by the name of the function, and the dependencies are determined by the parameters. So it's this sort of simple thing. If you've ever seen PyTest, it has that exact same pattern, just sort of applied and taken to a further extent. So it replaces code that looks like this instead of writing sort of these common data frame transformations. And we're going to use pandas, but it can really do anything here. You declare these functions, right? Where the output is the function name and the input is the function argument. So it's just as simple as this. Every transformation becomes a function. So what does this look like altogether? Well, you got your functions, and then you got a driver that says what and when to execute. So we're importing this sort of feature logic model we defined above, instantiating the driver, passing it some initial data, and then executing it, just executing the pieces we want, right? So we get to delayed execution and finally outputting them somewhere. So to sum this all up, for each transformation, you write a function. Functions declare a directed acyclic graph, and Hamilton handles DAG execution. You're probably all familiar with DAGs, but if not, there are a bunch of things that it can model. In this case, it's just modeling a computation flow, right? So C gets executed before D, the results of C are passed into D, etc. Cool. So you might be curious, doesn't Hamilton make your code more verbose? I want to say yes, but that's not always a bad thing. And so instead of writing these like simple transforms in pandas data frame, you're writing whole functions, but you get a lot out of this. So code is read often 10 times as much as it's written. And the verbose sort of very clearly written code is probably better than the super sort of short code that's harder to read. But when it is a bad thing, we have all sorts of decorators that add extra metadata and whatnot to these functions. So there's tag that attaches metadata, parameterize, which sort of like repeats a function. It's like kind of like a for loop. Extract columns, which takes a function that outputs a data frame, and multiple series, and data validation. And we have quite a few more of these. So how does this work together with federated learning? Bless you. The approach is pretty simple. You use Hamilton to share code. Given that everything's written in sort of the standard way, it's a really clean way to sort of share between different implementations of feature engineering. You can swap out implementations between collaborators. So if their data is in different shape, you choose which one to use per collaborator, and each one sort of implements their own pieces, but then has sort of some common piece. And then you can track versions, manage, and assert sort of compatibility on the Flower side, on the training side. So if one organization is using the wrong version of your feature transforms, you can break when they're all together, or when it's combined, before you sort of train a whole model and waste all the carbon output of 300 EU households. So it's a really cool talk. All right, so what is it? So let's start with sharing code. The idea is that you have common modules between teams and organizations, and a data contract is specified by the DAG inputs, right? So we've got a features.py, which has all the sort of feature transformations. I made this like really generic looking. You got your sort of transformations and training data. The point is you can build this to be whatever you look like, and everybody's is different. And then you've got the training side, which just does some like flowery stuff. I hand waved this a bit, but I've been messing around and like toying around with Flower, and I'm pretty excited about the ways that it could work together. Then each hospital sort of is using the same thing here. And you got this data contract specified by the DAG inputs, right? So they all take in something that I called a bit on the nose sensitive data. All right, so the really cool thing is this allows you to swap out implementations. So you can have the common feature transformations between teams and organizations that all have sort of a data contract, right? These all depend on this sensitive data. It's the series, it should probably be a data frame. And then if people want to load their sensitive data in, they can implement their own version of doing that, right? And the really cool thing you can do is you can use the validation decorator to ensure that the output of the training data matches some schema, right? So that you ensure on the client side, they're using the right data. So the TLDR here is we are having organizations work on some of the same code and then writing their own. The piece that I'm not showing here is that in the driver, you can say, I want X, Y, and Z module, where Z could be common and X and Y could be specifically implemented. And X and Y could implement the same as, say, X prime and Y prime from another organization. Cool. So yeah, cool thing you can do with this is you can track versions. So you can easily get access to all of these things. Hamilton makes it easy, and there's a lot of inspect utilities. The Git hash, the code hash, etc. You can send over that sort of metadata along with federated learning in the client and assert that the versions are compatible on the Flower side. So you get sort of incompatible versions, you break on training. I hand waved this a bit, but I think this should be pretty easy to figure out the natural way to sort of take the metadata that Hamilton gives you and combine it using Flower. Cool. So tying this all together, teams collaborate on feature engineering with Hamilton code. They send shared data over to Flower. The data contracts are formed by these shared modules, and data validation is added by using sort of assertions using check output and potentially as well on the server side. So Flower solves distributing model training. Hamilton is the natural partner to ensure that your data is good, that you don't get garbage in, garbage out. All right. So I hope I gave you a whirlwind tour of how Hamilton and Flower could happily work together. The other thing I want to share is that by buying into the Hamilton paradigm, you get all sorts of additional benefits from the sort of software engineering practices, which is one of the things that we're really focusing on and interested in. So Hamilton lets you write transforms in plain old Python functions. And these Python functions provide everything you need to know. Unit testing is simple. They're plain old Python functions. Documentation, all you have to do is use the doc string. It's sort of self-documenting. They're naturally modular. They're broken into small pieces by definition. You naturally get a data catalog, so you know sort of like what data is available. Everything's written in Hamilton functions. The code forms a centralized feature definition store. Debugging is pretty straightforward. You can do all sorts of crazy, cool debugging tools where you sort of do binary searches to figure out where your data is weird. It's just a much easier way to sort of deal with complex chains of features. And you naturally get trustworthy data. We showed how validation works, but there are all sorts of tools in Hamilton that make it easy to trust your data. So a little bit about open source progress and updates. Early stages, but thriving community. A few exciting users. Meeting some of them tomorrow. We have a growing set of core contributors as well, and a full company, that's us, dedicated to building it. We're looking for contributors, bug hunters, and user feedback. We have a lot of exciting things in progress. So more expressive APIs to allow for easy loading and saving of data, and perhaps a decorator for loading up SQL. This could make it so an easy way to sort of like get your data from its store. And your idea here, we're accepting user proposals and contributions all the time. On the execution side, we're thinking about how to have Hamilton be sort of a general language that can kind of almost compile into the orchestration framework so that all you think about is a chain of Python functions and not the infrastructure to run on, and then we can just run it on that for you. We're looking at potentially generator support to allow for mini batch. I think this could be a perfect combination with Flower because it's just sort of a natural generator about go until we don't want to update the weights anymore. And as opposed to you sort of running it in a loop, we could actually naturally build that in Hamilton. And we're looking to improve our PySpark integration. And again, we're taking new ideas all the time. So I give Hamilton a try. We love your feedback. Go to tryhamilton.dev, install it, star on GitHub. I think there's an this talk was originally supposed to be on the industry day and then the train strike happened and the timing didn't work out. But I think there's a really interesting academic use case, and we have like the Department of Energy in the US using this to ensure sort of reproducible, clean, self-documenting pipelines. So super excited about that. Create and vote in issues on GitHub, star us on GitHub, and join us on our Slack. And here's how to contact me. Linktree, it'll be available in the YouTube afterwards. Thanks, folks. Appreciate your time.
I was wondering when it comes time to try to make sure that the ML development pipelines are sort of in good shape. Mm-hmm. Do people have sort of what's the main kind of thing that people fall over if they weren't using something like Hamilton?
Yeah, so there's a lot of pieces to it, but you'll end up like in a position where one person wrote sort of a very complicated ML pipeline. It's got a bunch of transforms, and then they leave the organization or they go over to another research project, and the next person inherits it. So you just I think just confusion and onboarding is probably the biggest thing that we're trying to solve with this project. I didn't even tell the origin story of it, but it came from a time series transform at Stitch Fix where I used to work. They had like 4,000 features that they were doing time series transformations on, and they were like predicting the business. And to add a new one, the business always wanted something, so to add a new one, it became nearly impossible because nobody really knew how it worked. There was one person who knew how everything worked, but like they didn't really care enough to sort of jump in and fix it. So it was kind of a pain. So I think that's the
main thing.
Yeah, that's the main thing.
Yeah. Okay. Cool.
There's a question from Zoom. SK asks, isn't Hamilton just contract-based programming that most have been using as part of software development practice? And because of program agnostic nature of development, isn't that available anyway? What additional value does Hamilton provide?
Yes, it is just contract-based development. I mean, that's one of the things it does, but it makes it so you don't have to think about the contract, right? So you can define it once and then not worry about it later. Like you could ask, like, isn't this just X, isn't this Y? And it's like, yeah, it's a framework that one of the many benefits it has is to do that specifically. So it's a good question.
Yeah. Okay, cool. Well, yeah, thank you again.